Hi, this is Dr. Bay, and here's Bugsy. And today we're going to go over carbocation stability and various carbocation rearrangements. So stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly we fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Recall that carbocations are carbon atoms that only have 3 bonds connected to it with an overall formal charge of +1. There are several types of carbocations, and some are more stable than others. Methyl carbocations that contain 0 beta carbons are least stable. And as you increase the number of beta carbons, the carbocation's stability also increases. So tertiary carbocations with 3 beta carbons are the most stable type of carbocation. And one thing to remember is that carbocations have a trigonal planar geometry, so they are all planar or flat. Carbocations are stabilized by resonance. Adjacent carbon-carbon pi bonds stabilize carbocations because the overlap between the empty p orbital of the carbocation with the p orbitals from the pi bond allow for that positive charge to be delocalized or shared between multiple atoms. Here are a couple of examples comparing carbocation stability. In the first example, the benzylic carbocation is much more stable than the molecule to the right because the benzyl group allows for resonance to occur. In the second example on the right, the allylic carbocation also allows for resonance to occur, which is why it's more stable than the butane carbocation. And in the bottom example, the left structure is more stable because it can form more resonance structures than the allylic carbocation shown on the right. And remember that the more resonance structures it can form, the more stable the molecule is. Secondly, carbocations are stabilized by adjacent atoms with lone pairs of electrons. The donation of a lone pair by the adjacent atom allows for the formation of a new pi bond, creating a stabilizing resonance contributor. In all of the examples down below, the more stable carbocation contains the possibility for more resonance structures to form. Now let's connect the concept of carbocation stability to an SN1 reaction. Recall that SN1 is a two-step mechanism where first the leaving group leaves to form a carbocation, then a weak nucleophile attacks the carbocation, and then a proton transfer occurs to form the final product. But in the second example, the position where you would expect the OH group to add onto is at a different carbon location than where the original chlorine leaving group was in the substrate. So how did this happen? So, surprisingly, carbocations can actually rearrange to form a more stable carbocation. And there are two main types of carbocation rearrangements, a 1,2 hydride shift and a 1,2 alkyl shift. In a hydride shift, the bond of an adjacent hydrogen moves to the carbocation, and this rearrangement then moves the carbocation to a more stable tertiary position. In this next example on the right, the hydrogen bond can move to the carbocation position, which thus forms a secondary allylic carbocation, which is much more stable than the original secondary carbocation. And in a 1,2 alkyl shift, you can move a carbon-carbon bond to also form a more stable carbocation. So let's draw the arrow-pushing mechanism for the following reaction. Since both the nucleophile and solvent are water, this means that the reaction will go through an SN1 mechanism. The first step is for the leaving group to leave, and this forms the carbocation intermediate. And then a 1,2 alkyl shift will occur to move a methyl group to the carbocation, and thus forming a new tertiary carbocation that is more stable than the original secondary carbocation. And then from here, water acts as a nucleophile and will attack the carbocation. Then a proton transfer occurs where Cl- deprotonates the hydrogen, which then gets us to the final product. So in summary, tertiary carbocations are most stable, while methyl carbocations are least stable. And carbocations can be stabilized by being adjacent to pi bonds, aka allylic and benzylic positions, and they can also be stabilized by lone pairs through resonance. And carbocations can also rearrange to form a more stable carbocation through either a hydride shift or an alkyl shift.
Organic.